बिस्मिल्लाहिर्रहमानिर्रहीम। वेलकम बैक टू मैथमेटिकल मेथड्स ऑफ फिज़िक्स। आज हम इसका लेक्चर नंबर 11 देखेंगे। इससे पहले हमने लेक्चर नंबर 10 में जो किया उसको रिव्यू करते हैं। वी कंस्ट्रक्टेड बेसिकली द ग्रीन्स फंक्शन फॉर सेकंड ऑर्डर बाउंड्री वैल्यू प्रॉब्लम्स। Basically we took the second order differential equations and we solved them to construct the Green's functions for different kinds of with different boundary conditions basically. So we had homogeneous equations, homogeneous boundary conditions, and we solved the Green's function. The Green's function essentially satisfies the same differential equation with the same boundary conditions. Only thing is the operator, the differential operator is the same, but the right hand side we replace it by the Dirac delta function. Then we impose two additional properties, additional conditions on the Green's function. One is the continuity condition and the second is jump discontinuity of the derivative. So if you remember everything, we have I think done 3 examples as well very thoroughly, and if you have gone through that lecture very carefully, you must know what we did with the Green's function. So we will continue with the Green's functions today, and we will use a slightly different method to construct the Green's function. So again, constructions of Green's function using the method of variation of parameters. So we will construct the Green's function using the method of variation of parameters, and then we will see some examples. So let's start with the construction of Green's function using the method of variation of parameters. Consider the following linear non-homogeneous second order differential equation. Again, this is a non-homogeneous now. If you recall, last time we considered the homogeneous second order differential equation where the right hand side was 0, but here right hand side is f of x with the homogeneous boundary conditions. So still we are taking the homogeneous boundary conditions at a and at b, where of course alpha 1 alpha 2 simultaneously cannot be equal to 0, beta 1 and beta 2 simultaneously cannot be equal to 0. Assume that px, qx and fx are continuous in the interval a to b. So these functions px, qx and f of x, they are continuous. The homogeneous part of this colored equation is this one, like the corresponding basically homogeneous equation. If we take this fx to be equal to 0, it's called the homogeneous part of this equation, or the homogeneous equation corresponding to this equation, right? We have the same left hand side equal to 0. So this is the homogeneous equation. Now if we solve this homogeneous equation, the general solution of this homogeneous equation will be called the complementary function of this equation, this non-homogeneous equation. So the complementary function of this equation is a y1x plus b y2x, where y1, y2 are any solutions of this homogeneous equation. Alright? If you recall, we know we had usually for constant coefficients case we have like the the roots of auxiliary equation gives you these y1 and y2. Alright? So here y1 and y2 are two linearly independent solutions of the above homogeneous equation, and a and b are two arbitrary constants. Now to obtain the general solution, we vary the parameters a and b such that, that's why we call it a variation of parameters, right? We vary parameters a and b and call them ax and bx instead of a and b. We call them ax. Let's make them dependent on x. So using the method of variation of parameter, we assume the following two equations, that a prime x y1x plus b prime x y2x should be equal to 0, and a prime x y1 prime x b2x y2 prime x equal to 0. So if we solve these two equations for a prime and b prime, you get this one. A prime is minus y2f over w, and b prime is y1f over w, where w is the Wronskian of y1 and y2. W is the Wronskian of y1 and y2. So if you define Wronskian, Wronskian is y1, y2, y1 prime, y2 prime, right? This is the Wronskian of any, and because y1 and y2 are linearly independent, this Wronskian has to be non-zero. If they are linearly dependent function, this Wronskian comes out to be 0, and these two expressions are not defined. These two red equations will not be defined. Alright, so W has to be non-zero, and this linear independence of these two solutions guarantees that W will be non-zero. Alright, so these two are defined equations, and now we can integrate them to find A and B. Once you get A and B, plug them into here in blue equation, you get another y of x, which is the solution. We call this the particular solution of the equation. So upon integration, the colored red equations become these red equations, right? Become this one. You can integrate them from a constant to x, You get this one, where c1, c2 are constants, can be determined from the boundary conditions on ax and bx respectively. Thus the values are c1 is equal to a and c2 is equal to b. A little exercise for you: if you really use the boundary conditions on ax and bx, which are these conditions, right? If you use them, you will get A and B. So basically AX is from A to X, and BX is also from B to X. So you can integrate them and find AX and BX. So once AX and BX are known, you see X has to be less than B, because X always lies between the interval A and B. So C2 comes out to be B, so it has to be B to X, right? But a smaller limit should be the lower one. So we can change the limits x to b and put a minus sign up front. So here you see, I put the minus sign up front and wrote it like x to b, because b is bigger than x. So it has to be upper limit. So changing the sign of integral. So now you can substitute the values of ax, it's not s, ax and bx in the blue equation here, ax and bx here, to find yx. So your yx is this one, and if you combine them, you see it's almost the same. y1x, y2 eta, and y1 eta, y2x by changing. So if I define a Green's function or any function like this one, that from a to eta, if eta is from a to x, then this is our Green's function, and if eta is from x to b, right, then this is your Green's function. So you took this as one, where x is from eta to b, right, and here your x is from eta to a to eta. Alright, so this is the case. So we can then combine it and write it as from a to b, because we replace these two functions by the Green's function. So a to b, gx eta, f eta, d eta. So again you see this is kind of integral equation again, right, integral equation. So but this is a known, yx is known here because g is known, f is known, then this is your solution. It means that if the Green's function basically is known to you of this differential equation, then the solution of the non-homogeneous equation is very simple. It can be determined from Green's function times f eta and by the integration. Alright? So some remarks here, that gx eta satisfy the boundary condition of the problem. Of course, if you look at the boundary conditions, this g eta will satisfy the conditions. Gx eta is continuous function at x is equal to eta. If you take at x is equal to eta, this is a continuous function. Alright? You can easily prove the continuity here. Except at eta, gx satisfies the homogeneous form of the given differential equation. Since y1, y2 are solutions of the equation, alright, because y1, y2 are both solutions, then this also satisfies the homogeneous part of the equation, because we know that to find the Green's function, what we do is we take g double prime plus px g prime plus qx, g is equal to delta x minus eta. So apart from x is equal to eta, so if x is not equal to eta, we have the homogeneous equation for Green's function, and that Green's function will satisfy the homogeneous equation. That's why we wrote here except at x is equal to eta, because at x is equal to eta, the right hand side blows up. So whenever x is not equal to eta, then gx will satisfy the homogeneous equation. The following equation, which is just the solution, we obtain it here, this one. This equation must satisfy the given differential equation, which means must satisfy the given differential equation, which means if we replace this one in our equation, it should give you f of x. Alright, so now if you replace this into your equation here, in this equation, if you replace the expression y, which is of the integral form, replace it here, and after some simplification you will arrive at here. Now this thing is nothing but the same differential equation with the Green's function, and we know that the Green's function satisfies the same left hand side, but the right hand side should be equal to the delta x minus eta. Alright, so if we replace this by delta x minus eta, the answer should be f of x. Because whenever you take the integral of delta with some function, it picks up the value of the function at x is equal to eta, or eta is equal to x. Alright, so of course this will satisfy your differential equation very easily. The quantity under bracket must be 0 except at eta, and thus it follows this differential equation. And we know that whenever we replace left hand side by g, the Green's function, the right hand side is replaced by the delta function. Alright, so these were few remarks for your Green's function and the formulation. For gx, we know that the derivative of g with respect to x should have a jump discontinuity, right? Should have a jump discontinuity. So if we differentiate our function with respect to x, this is what we get, because only the x part will get differentiated, the eta part will remain there. Alright, and if you take the jump here, partial g by partial x at eta plus and partial g by partial x at eta minus should be equal to this at eta plus means at eta, right? And here again at y1 prime, y2 prime at eta should be equal to -1. Alright, so you got this basically this condition basically which has to be equal to -1. This result can also be obtained by integrating your original Green's function equation. If you integrate this once, you will exactly arrive at this condition, which is -1. And we know that the Green's function always satisfies this jump condition, downward jump. So this jump condition can also be obtained by integrating the Green's function equation. That is very easy. We have done this in the last lecture, so it's similar. The Green's function obtained through this procedure may or may not be symmetric. I think we made this remark last time as well. In our examples, it was a symmetric Green's function, but it's not necessary all the time. There are physical problems where Green's function come out to be non-symmetric. Alright, so this is not the property all the time. Usually it comes out to be a symmetric function. So now let's consider the second order non-homogeneous differential equation y double prime plus pxy prime plus qxy is equal to f of x with the homogeneous boundary conditions x equal to a and x equal to b. These are the homogeneous boundary conditions where alpha 1 alpha 2 both are not 0, and similarly beta 1 beta 2 cannot be simultaneously equal to 0. Consider a particular solution which satisfies the above differential equation in the following form. And we have just obtained this equation by method of variation of parameters. So we can say that this is the particular solution of this above differential equation, right? Where g satisfies because g is a Green's function, so it should satisfy the same differential equation, right hand side replaced by the delta function. Alright? With the following properties, what will be the properties on g? That g will satisfy the same boundary conditions. Additionally, g should have a continuity condition. This is a continuity condition. At x is equal to eta, gx eta is continuous in this interval, and jump condition is this one, which is the same. I wrote it twice, it's a mistake. Continuity condition is that gx has to be continuous at eta, but jump discontinuity is partial g by partial x at eta plus and minus partial g by partial x at eta minus should be equal to -1. Then a particular solution of the given boundary value problem can be obtained as this one, where g is called the Green's function of the problem defined by the given differential equation and its boundary conditions. We will follow this process now to obtain the Green's function by using method of separation of variables. Alright, so next we move on to the examples, and we'll do 2-3 examples to reinforce the ideas. Alright, so let's see some examples of the construction of Green's function using the method we just developed. So we'll see these two examples. In first example, we will find the Green's function for the homogeneous boundary value problem, and finding the Green's function is almost exactly the same which we did in the last lecture, but then we will use the Green's function to obtain the particular solution of this non-homogeneous equation. Alright, and similarly we will do the same for the second example. So first we need to find the Green's function of this example. Then we need to solve the same equation with right hand side minus 3 sine 2x. Alright. So with the help of this Green's function, I will be solving this one later on. Alright. So to construct Green's function, gx theta must satisfy first of all g double prime plus g is equal to minus delta x minus theta, right? And then with the same boundary conditions, that g at 0 eta is equal to 0 and g at pi eta is equal to 0. Then we have a continuity condition that g of eta minus should be the same as g of eta plus. Right? When x is eta minus x is eta plus, it has to be equal to 0. And jump condition was that partial g by partial x at eta plus minus partial g by partial x at eta minus has to be equal to negative 1. Alright? So these are all conditions which will be satisfied by the Green's function. So let's first solve this Green's function, and again we have to solve it when x is not equal to eta. We have g double prime plus g equal to 0. So from here, if we write the auxiliary equation, it is m square plus 1 is equal to 0. So m is equal to plus and minus iota. So this implies g is equal to, g has the form c1 cosine x plus c2 sine x. Alright, so therefore we can have gx eta, because we need to define it for the two intervals x less than eta and x greater than eta. So this will be equal to a cosine x plus b. We need to change the coefficients, so this is when x is between 0 and eta, and then c cosine x plus d sine x when eta to pi. Right? Our conditions are from 0 to pi, so that's why we are having pi here. Now use boundary conditions. If we use boundary condition, we can replace these 4 coefficients to 2. So first condition is that g0 eta is equal to 0. It means a cos 0 is 1 plus b sine 0 is 0. So that is equal to 0, implies that a is equal to 0. Similarly, g at pi eta is a cosine pi is negative 1 and b sine pi is again c negative 1 and d 0 is equal to 0. So this implies that c is equal to 0. So therefore your Green's function reduced to 2 coefficients, that a is 0, so it becomes b sine x, and c is 0, so it is d sine x. X from 0 to eta and x from eta to pi. Alright, so this is what we got. Now continuity condition. Continuity says limit x goes to eta plus g should be equal to limit x goes to eta minus g has to be equal. This is the same as writing eta plus eta and g of eta minus eta. Alright, so this is the same thing. G of eta plus is this, basically that x is bigger than eta, that is d sine x. So d sine x at x is equal to eta, and this is b sine x at x is equal to eta. So that is d sine eta is equal to b sine eta. So this implies that d is equal to b. If d is equal to b, then you can call it, let's say, alpha, right? So therefore g becomes, so g x eta will become alpha sine x and alpha sine x. So now we can use the jump discontinuity. Minus partial g by partial x, eta minus should be equal to -1. So if you take the derivative, it is alpha cosine x, eta alpha cosine x. So for x is equal to eta, not equal to eta, our g should satisfy this equation. So from here it's clear that auxiliary equation gives you the roots m square plus 1 equal to 0. So m will be equal to plus minus iota. So our g of x eta should have this form: a cosine x plus b sine x, and c cosine x plus d sine x in different intervals, that is x from 0 to eta and eta from x from eta to pi. Alright, so now using the boundary conditions, boundary condition is g at 0 is 0. So this implies that a cosine 0 is 1 and b sine 0 is 0 is equal to 0. So this implies a is 0. So one coefficient is gone. Second condition is g prime. So g prime means partial by partial. What is our second? This is g prime, partial g by partial. So this condition is not. This one is partial g by partial at x pi eta is equal to 0. Because it's y prime at pi is equal to 0. So you have derivative is with respect to x. So derivative of g with respect to x is partial g by partial x at pi eta. Alright. So partial g by partial x at pi eta is equal to, this is the derivative. So it will come from c minus c sine pi plus d cosine pi is equal to 0, and here cosine pi minus c sine pi is 0 and d cosine pi is -1. So this implies that d is equal to 0. Alright, so our Green's function reduces to, therefore our Green's function will become a cos x, and a becomes 0, so it is b sine x, and c cos x and d became 0, so c cosine x. So this is what we are getting. Alright, so now continuity of g. We again don't have any issue between 0 and eta to pi, because both sine and cosine are continuous functions. So only problem, only worry is at x is equal to eta, whether this is continuous at x equal to eta or not. So for that we should have eta plus or eta minus g should be equal to limit x goes to eta minus g. Alright, so if you take this one, this is c cosine eta and this is b sine eta, right? And if you divide by sine eta here and cosine eta there, so this is c by sine eta is equal to b by cosine eta. So let's call it alpha, say, then our c becomes alpha sine eta and b becomes alpha cosine eta. So I replace b and c. B is alpha cosine eta. So then our Green's function will take the form alpha cosine eta sine x and alpha sine eta cosine x. So I replace the values of b and c. Now using the jump condition, jump of partial g by partial x, basically at x is equal to eta plus minus partial g by partial x at x equal to eta minus is equal to -1. Alright, so now if you do this one, the derivative of g with respect to x is at x, eta plus is this basically, so alpha sine eta, and the derivative of cosine x is minus sine x, so it will be minus sine eta, minus partial g by partial x. Now here it is alpha cosine eta, and the derivative is cosine x, and at x equal to eta, it's eta equal to -1. So this is minus alpha is equal to -1, implies that alpha is equal to 1. So I got the value of alpha as well. So therefore our completely determined Green's function came out to be cosine eta sine x ठीक है, तो ये आपके पास ग्रीन्स फंक्शन आ गया. I think it's the same example which we did, not exactly the same, but it's very similar example that we did in the last lecture. So it's nothing new for you guys, it's the old thing. New thing is that now we have to use this Green's function to find the solution of the non-homogeneous equation, right? So we use this gx eta to find the solution of non-homogeneous equation. Y double prime plus y is equal to -3 sine 2x with the same boundary conditions. Alright, so this is what we have, and if you recall what we had, the solution is, recall y is equal to minus a to b g x eta f eta d eta is the solution, right? This is your particular solution, right? So this is the solution, but here in our case a is 0, b is pi, f is -3 sine 2x. Alright, so these are the things. This is your f, and our a and b are from 0 to pi. So therefore y is equal to -0 to pi Green's function, and f eta is -3 sine to eta d eta. Now because Green's function is defined on the different intervals from 0 to x and x to pi, this is the same as saying eta goes from x to, because x is greater than eta here, so it has to be greater than eta, but eta cannot go beyond pi. Here is similarly eta is less than x, so eta is less than or equal to x, but it cannot go below 0. So these are the alternate limits you can use. Why I am writing these two limits? Because here it's the values of eta. If I write it from 0 to x, and then from x to eta, x to pi, right? Eta, then these are the values of eta. Eta goes from 0 to x, so it means eta is between 0 and x. So I have to define where eta lies. Eta between 0 and x, so I will pick this function for the first integral, and eta goes from x to pi, so I will pick this for the second integral. Alright, so sine eta cos x in the first interval, here it is sine eta cosine x. Alright, so similarly this is cos eta sine x. So now this -3 and minus will become +3, so this is +3 0 to pi, it is sine eta cosine x times sine 2x dx, and similarly it will become +3 from x to pi cosine eta sine x times sine 2x d eta. This is eta, this is eta, this is also eta. Alright, so this is what we got. We replace the value. Here minus 3 make it plus 3 outside. So this is cos eta sine x, sine eta cos x. Alright, so this is what you got, and this is x as well. Alright, so that's what you got. Now we have to integrate. Cosine x is constant. We can, because we are integrating with respect to eta. So cos, we can bring cos x outside. So 0 to x, this is sine eta and sine 2 eta. What is sine 2 eta? Sine 2 eta is 2 sine eta cosine eta. Alright. Similarly, plus 3 sine x is outside from x to pi. So this is cosine eta, and sine 2 eta is again 2 sine eta cosine eta d eta. Alright. So now we have 3 cosine x, 0 to x. This is 2 comes out, so it will become 6 cos x. So we have sine square eta cosine eta d eta. Similarly here it is 6 sine x, and inside now you have cosine squared eta and sine eta d eta. So now you see we have the derivative of sine x inside. The derivative of sine is cosine, so it will become sine cube eta by 3 from 0 to x. And here I will need minus sign. Why I need minus sign? Because the derivative of cosine is negative sign, so that negative will make it negative outside, and this is cos cube eta by 3 from x to pi. So now if you replace the values of eta is equal to x, so eta is equal to x makes it sine cube x, and minus sine 0 is 0. This 3 is cancelled with this 2, so you can write 2 here, and minus again 3 times 2 is 6, so you can write it minus 2 sine x, and cosine cube pi minus cosine cube x. And what is cosine cube pi? It's negative 1. It's negative 1. So you got 2 cosine x sine cube x minus plus 2 sine x cosine cube x, and minus plus 2 sine x. I wrote this term at the end. This term is at the end here. So cosine cube pi is negative 1. So negative plus 2 sine pi. I wrote this before. So here 2 sine x cos x is common. So inside will become sine square x plus cos square x. So 2 sine x cosine x is common. Inside you will have sine square plus cosine square x plus 2 sine x at the end. So this is 1. So you got, and this is sine 2x, right? So you got sine 2x plus 2 sine x. So this is your particular solution of the equation. Alright, this is the particular solution of the, so this is the required particular solution of the non-homogeneous equation y double prime plus y is equal to minus 3 sine 2x. So we used integral definition of the particular solution to obtain the particular solution by using the Green's function. Alright. So this is our one of the examples. So we just solved this non-homogeneous system with the help of the Green's function of the non-homogeneous equation with the same boundary condition. So next we have this example. Find the particular solution of the following boundary value problem by using the Green's function method. So y double prime is negative x, y0 equal to y1 is equal to 0. Alright, so let's solve this example now. Y double prime equal to negative x, and y at 0 and y at 1 is equal to 0. Alright, this is our equation. So again, to solve this equation, what we need to do is the Green's function will satisfy the following, that G double prime is equal to minus delta x minus eta. We replace the right hand side by the delta function, that's it, no matter what the right hand side is. Alright, subject to the boundary conditions that G0 eta is equal to 0 and G1 eta is also equal to 0. Continuity, that G as x goes to eta plus and G as x goes to eta minus should be same. Right, this is a continuity condition, and then this is a jump. There is a jump condition that partial G by partial x at eta plus minus partial G by partial x at eta minus should be equal to -1. So again, these are the conditions which this Green's function will satisfy. So first of all, if x is not equal to eta, then the differential equation is 0. G double prime is equal to 0 because delta is equal to 0 whenever x is not equal to eta. So from here, G is, if we integrate it once, I will get C1, integrated second times C1x plus C2. Alright, so therefore our Green's function as gx eta has this form, ax plus b and cx plus d. We have to write it twice. We have to write it twice. The reason is, we have to write at the both sides, x less than eta and x greater than eta. So for both the cases, the form of the Green's function is the same. So that's why we have to write the same form for x less than eta and for x greater than eta. Alright, limits are from 0 to 1. Now if we use the boundary conditions, boundary condition is G0 eta is equal to 0. So it means A is equal to 0. No, A at 0 plus B is equal to 0, so it means B is equal to 0. And G at 1 eta is equal to 0 implies that C plus D is equal to 0, so this implies that your C is equal to -D. Alright, so therefore your Gx eta became Ax because B is 0, and C is equal to -D, or you can call D is equal to -C, whatever you want to call it, right? If I replace D by -C, then this is D times 1 minus x. What I did is, okay, I replace C by -D. So if you take D as common, it will be minus x plus 1, so it's 1 minus x. Now from 4 coefficients, A, B, C, D, you have just 2, A and D. Now we use continuity. Again, you see Ax and 1 minus x, they are continuous function no matter what. These are polynomials, they are always continuous. So we may have a problem when x is equal to eta. So continuity at x is equal to eta gives you limit x goes to eta minus g, limit x goes to eta plus g. Eta minus g gives you a eta, and this gives you d times 1 minus eta. Alright? So if you divide 1 minus eta here and divide eta on the right hand side, this is what you are getting. So let's call it alpha. So a is equal to alpha 1 minus eta, and d is equal to alpha eta. So therefore your Green's function takes the form a is alpha 1 minus eta x, and d is alpha eta and 1 minus x. Alright, so this is what you got. Alright, so now alpha is unknown now. So to find alpha, we can use the jump condition. Alright, so if I use the jump condition, that is partial g by partial x at x is equal to eta plus minus partial g by partial x at x is equal to eta minus should be equal to -1. So this is the jump condition. So if you use this jump condition at eta plus, what is the derivative? At eta plus it is minus alpha eta because the derivative is -1. Alright, so negative alpha eta minus the derivative at eta minus is alpha times 1 minus eta times 1. So it is alpha times 1 minus eta. that is minus 1. So minus alpha eta minus alpha plus alpha eta is equal to negative 1. They are cancelled, so alpha comes out to be equal to 1. So therefore the final Green's function takes this form. Alpha is 1, so you got 1 minus eta x and 1 minus x eta. All right. So this is what you got as the final form of the Green's function. Now the question was, use the Green's function. This is our equation. Use the Green's function to find the particular solution of this equation. Right? So for the particular solution, I need to take this as f of x. All right? So the particular solution of y double prime is equal to minus x is y is equal to negative 0 to 1 gx eta f eta d eta, where f is equal to minus x. This is your function on the right hand side. So what I will do is, we have to first of all break it from 0 to x. This is d eta, and minus x to 1 gx eta f eta d eta. Now the Green's function from 0 to x, when eta is from 0 to x, eta is from 0 to x. So this is basically, this is the case when eta is 0 to x. Here you see, because eta less than or equal to x, and it cannot go below 0. So you have to use this function when eta is less than x. So when eta is less than x, it's 1 minus x eta. When eta is less than x, it's 1 minus x eta, and your f eta is minus eta d eta. And similarly, when eta is greater than x, your Green's function is 1 minus eta x, and function is minus eta d eta. All right. So now bring 1 minus x outside. 0 to x eta square d eta. Again bring x outside, x to 1. It's minus minus plus, you can write it. So this minus and this minus is 1. So x is out, so eta minus eta square. So this is what you got. So now if you integrate, you will get 1 minus x is outside, and eta square is eta cubed by 3 from 0 to x, right? Eta cubed by 3, and here it's eta square by 2 minus eta cubed by 3. From x to 1. So you got 1 minus x, x cubed by 3 plus x, it's 1 by 2 minus 1 by 3, and minus x square by 2 plus x cubed by 3. Alright, so this is what you got. So now if you simplify, this is x cubed by 3 minus x 4 by 3 plus 1 by 2 minus 1 by 3 is 1 by 6. So x by 6 minus x cubed by 2 plus x 4 by 3. So this x 4 by 3 is gone. With this x 4 by 3, so you are left with x cubed by 3 minus x cubed by 2. It's x by 6 minus 1 by 3 minus 1 by 2 is minus 1 by 6. So minus x cubed by 6. So if you take x by 6 common, it is 1 minus x square. So this is the particular solution, right? So this is the required particular solution of the non-homogeneous equation which was, I guess, y double prime equal to minus x. All right, subject to. All right, so conditions don't matter, of course. In the interval 0 to 1 only matters. So in these two examples, what we did is we constructed the Green's function, and with the help of that Green's function we obtained the particular solution of the non-homogeneous differential equation. All right, so in both the examples we did the same thing. All right, so this is these are the two examples which we solved. We basically used the homogeneous part to construct the Green's function, and then we used that Green's function to find the particular solution of the non-homogeneous equation. Same thing we did here is we considered the homogeneous part of this to construct the Green's function, and then we used that Green's function to obtain the particular solution of the non-homogeneous equation by taking this fx into consideration. All right, so today we did a construction of the Green's function using method of variation of parameters. Basically, we constructed Green's function with the same way as we did in the last lecture, but we used method of variation of parameters to obtain the particular solution of the differential equation with the help of Green's function. So we formulate, let me go back and give you that idea here. Here, basically, for this equation, for this non-homogeneous equation, we used method of variation of parameters to construct the Green's function, like this one. And once the Green's function is there, we constructed this y of x. All right. So basically, here in those two examples which I did at the end, I obtained Green's function explicitly. All right, I obtained Green's function explicitly. But what you can do is you can actually use this formula to write the Green's function. If you want to save your time, you can construct the Green's function by using y1 and y2, and then you can use this one to find your particular solution. So y1x, y2 eta, y2x, y1 eta, and divided by the Wronskian. y1 and y2 are the solutions of corresponding homogeneous equation. All right. So if you can find two solutions, y1 and y2, from the corresponding homogeneous equation, you can easily obtain your Green's function from there. So if let's say cosine x and sine x are your Green's function, then of course cosine x and sine eta cosine x will give you your equations. So let's use this formula to find the Green's function. And if you don't want to find the overall thing, for the same example here, what was your y1 and y2? Basically, these are the solutions of the homogeneous equation. Solution of the homogeneous equation comes from the auxiliary equation. M square is equal to plus minus iota. So you got cosine x and sine x. y1 is cosine, y2 is sine. All right. So if you replace in this equation, y1 is cosine. So cosine x sine eta, and this is cosine eta sine x. All right, and what is the Wronskian? Wronskian is your cos x sine x, cos the derivative of cos, derivative of sine. If you take the Wronskian, it will come out to be 1. All right, so Wronskian is 1. So if you use this formula directly, you get the same Green's function which we obtained for this example. Exactly the same Green's function, which was cos eta sine x, sine eta cosine x. Similarly here, what is your what are your two solutions? Y double prime is equal to minus x. So c1x plus c2, so 1 is x and 1 is 1. All right. So if you take the if you take the auxiliary equation here, it's m square is equal to 0. Right. So m square equal to 0 means your m is 0. 0, it's a repeated case, so your solutions will be constant e to the power 0x times constant plus e to the power 0x times constant times x. All right, so your 1 and x are the solutions, and from there you can obtain your equation. Wronskian will be 1x and 0 1, so Wronskian will be 1 again in this case. Alright, Wronskian will be 1 here, and if you replace in the formula y1x y2 eta, I am sure that you will get the same Green's function which you obtained it here. So this is it. We developed a formula for the particular solution which is of the integral form. Y is equal to minus a to b g of x eta f eta d eta with the help of the variation of parameters method. We use the variation of parameter methods to get the integral formula for the particular equation, but that solution consists of a Green's function that contains Green's function. So once your Green's function is known, you can use that formula to obtain the particular solution of the non-homogeneous equation. So that is it for today's lecture. We carried on with the Green's function formulation, but with the help of Green's function today we solved non-homogeneous equations as well, and we saw a couple of examples very thoroughly. I hope you understood the topic, and I hope you will do a little practice to reinforce the ideas which we learned today. With that, I will take the permission to leave. Assalamu alaikum and Allah Hafiz.